Okay, so since we're going to be doing a week on the unit circle next week, I thought it might be a good idea for me to take a second and explain to you maybe a little bit about what is the unit circle and then, if possible, why it's important. And so the the first thing that's important to know about the unit circle is that it's a circle, and there are other things that are important to know, but one of them is that there's an equation, x squared plus y squared is equal to 1. That's the equation that lists all the points on the unit circle. There are infinitely many points on the unit circle, but we're often in pre-calculus and in calculus interested in specific points. And if you try to think of what those points are, well, it's a circle with a radius of 1. So I know a very kind of basic thing to do would be to list the points like this, which would be when x is 0, y is 1. When x is 1, y is 0. Or x could be negative 1 and y could be 0. Or y could be negative 1 and x could be 0. And that gives me a good basis for it. Now I have 4 points on the circle, but that's not enough. And in fact, there are a couple more that you might think. Like, one thing you might think of is, well, what if I go 1/2? What if I'm going to go just halfway to the 1? Where am I going to be at? And you might think you would be half on the y, but really, even my bad circle, you can tell that you're not at 1/2 on the y. You're actually closer to 1. And then so you might want to figure out, well, exactly what would that be? Well, the equation is x squared plus y squared is equal to 1. So I can do 1/2 squared plus y squared is equal to 1, which means y squared is equal to 1 minus 1/4, which is 3/4. So y is equal to the square root of 3 over 4, which is the same thing as saying the square root of 3 over the square root of 4. And the square root of 3 is an irrational number, so I'm going to just leave it like that. But the square root of 4 is 2. So now we've got one more point with 1/2, and I could have the square root of 3 over 2. That's this point right there. But actually, you could use some logic to realize that, oh, well, if I was at 1/2 on the y-axis, I would be at, the math would work the same way in this equation, except the 1/2 would go in for the y and not for the x. And so I would be at root 3 over 2. And so this guides us to, there's 16 points of interest on the unit circle that we keep coming back to. This guides us to 12 of those. The only other one is, what happens if I'm at the point, like if on the unit circle, let's say if I'm on this line, or this line really, what are these points right here? These 4 points, okay? Those are the points where x1 and y1 are equal. So those are 45 degrees. It's on the line y is equal to x. And so if I'm going to try to figure out what those points are, I could go back to my original equation and I could set it up. I'm not plugging in for either one of them, but I know since they're the same, I could write it like x squared plus x squared is equal to 1, which means 2x squared is equal to 1, which means x squared is equal to 1/2, which means x is equal to the square root of 1 over 2, which is the same as the square root of 1 over the square root of 2. And the square root of 1 is just 1. The square root of 2 is an irrational number. And we have this rule. I don't know where this rule comes from, but I did have a student that was always like, why is this rule the way it is, that somebody who was probably angry just decided at some point that you can't leave a square root sign in the denominator of a fraction. So we have this process called rationalizing the denominator, and it doesn't make the number look any more better than the way it originally did. But Now, because square root of 2 times the square root of 2 equals 2, the irrational part is in the numerator and not in the denominator. And while it may be arbitrary in many ways, it's important because it's convention. So now I have these points that all go together. And if I think of what does the unit circle look like, it's this circle. Let me try that again. It's this circle right here, and it's got these points on it, the ones we started with, boom, 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 boom. And now in each quadrant, it's going to have 3 more points. And if you add all these up, that works out to a total of 4 points per quadrant, which is a total of 16 points. If you want to know, go further into it, the angle from the origin to this first point is 30 degrees. The angle from the origin to the second point is 45 degrees. The angle of the origin to the third point is 60 degrees. And to the next one is 90 degrees. And to the next one (120). And then if I kept going around, it would be 150 degrees. Sorry, it would be 135 degrees, 150, 180, 210, 225, 240, 270, 300, 315, and 330. So the unit circle is the points, the coordinate, xy coordinate points that correspond to the angles that I just drew, that are 0 and then 30, 45, 60, and 90, but scaled to any different quadrant that you're in. And knowing the points, I'm going to show you why in a second, why knowing the points is important. It is a little bit like math to wait for the very end to tell you why it's important. But I'm just going to keep with convention here. So if I'm labeling these points, this is 1, 0. This point right here is the one that's going to be closer to 1 on the x-axis and closer to 0 on the y-axis. And if I'm remembering, I had these 3 sets of combinations. 1/2 went with root 3 over 2. Root 3 over 2 went with 1/2. And root 2 over 2 goes with itself. Those two numbers are kind of married to each other, so those are the only combinations that we're going to be using here. So this point is going to be root 3 over 2, comma 1/2. This next point is the point where they're identical, so that's root 2 over 2, comma root 2 over 2. This point is the flipped, so this is 1/2, comma root 3 over 2. This point is 0, comma 1. This point is closer to 1 on the y-axis, so it's root 3 over 2, comma 1/2. But then you have to remember that we were in quadrant 1. Now we're in quadrant 2. In quadrant 2, x is negative and y is positive. Then the next one is going to be negative root 2 over 2, comma root 2 over 2. And then the next one, that goes with this one right here. This one goes with that one. Then the next one is going to be flipped from the 120 degree one. So that's root 3 over 2, comma 1/2. Then it's going to be negative 1, comma 0. Now we're in quadrant 3, where both x and y are negative. So what's that going to be? If I look There's some symmetry here also. So these points, they have the same x value, and then they have opposite y values. So this is negative root 3 over 2, comma, negative 1/2. If I look at this point right here, they have going to be negative root 2 over 2, comma, and then I'm going to just take the opposite of that one. So negative root 2 over 2. And then same thing for this point right here. It's going to be negative 1/2, comma, negative root 3 over 2. And then you could also look at, there's symmetry when you look this way. So if I look in, now I'm in quadrant 4, and in quadrant 4, x is positive and y is negative. These 2 points that I've attached by a line right here are going to have the same y value, and they're going to have opposite x values. So this is quadrant 4. This point I forgot to say is 0, comma, negative 1. This point is going to be, what did I say, the same y value. So it's going to have negative, the same y value as this one right here. So it's going to have negative root 3 over 2. And it's going to have 1/2. And then this one's going to have the same y value, negative root 2 over 2 and root 2 over 2. And then this one is going to have root 3 over 2, comma, negative 1/2. So those are all the points that you have to remember. Now, the reason why it's important, one of the reasons why it's important is because, well, what we're after here is we're trying to figure out different triangles. So let me just take this triangle right here, for example. If I take this triangle right here and I call this theta, and I write it over here, well, we might remember that this is the opposite, this is the adjacent, this is the hypotenuse from trigonometry. And so if I was going to say the sine of theta, that would be opposite over hypotenuse. And if I was going to say the cosine of theta, that would be adjacent over hypotenuse. And if I wanted to say the tangent of theta, that's going to be opposite over adjacent. But what's interesting about this circle is that it's called the unit circle. The unit circle is the name of it for a reason, and the reason is because the radius of that circle is 1. So now if I go back to this triangle and put in 1 for all my hypotenuses, it actually makes it a little bit easier. So because I can just say that the sine of theta is just the opposite side. The cosine of theta is just the adjacent side. So encoded in all these unit circle coordinates are trigonometric operations. So we said that these things are going to be the frequently used angles. So let's say this is 30 degrees. The cosine of that angle is going to equal the x value. If you draw this triangle, by the way, this is the x value and this is the y value, right? This point is x comma y. And so the cosine of x, the cosine of the angle is going to be equal to x. So if I wanted to know what's the cosine of 30, I would look at my 30-point coordinate and I would look at the x values. So the cosine of 30 is equal to root 3 over 2. If I wanted to know what is the sine of 45 degrees, the sine of 45 degrees is not the one that I just highlighted, because the sine is not this one that's associated with the x coordinate. The sine of theta is associated with the y coordinate. Okay, so in any one of these coordinates, we have cosine of theta, comma, sine of theta. Theta is just another Greek letter that we use as a variable, mostly always to represent missing angles or unknown angles. So when I say theta, I'm pronouncing this letter right here. And if I'm looking for the sine of 45 degrees, now I can go to this coordinate right here because this is my 45-degree angle. And since it's sine, I'm going to look for this number right here, which is root 2 over 2. Now, in the past, you already had tools that could get you trigonometric values for the angles that are in the first quadrant. What you probably haven't done a lot with is angles that are in different quadrants, but we're going to start using those angles. So if I want to say, and if you're using just SOHCAHTOA, you don't think negatives have much of a place, but going forward, negatives do have a place. So if I said, what is the sine of 240 degrees? You would want to figure out, well, what is 240 degrees? 240 degrees is 0 plus 90 plus 90 more. That's 180. And then I need to go 60 more degrees. So this is 240 degrees. And I would want to know from this coordinate, which things got a little bit sloppy down here, but those are the xy coordinates that go with it. Since I said sine, I want to remember that sine is the y value. So sine of 240 degrees would be negative root 3 over 2. If I just kind of picked something at random and I said, what is the cosine of 315 degrees? You would want to tell me that 315 degrees is this angle right here. You could think of it as 45 less than 360. So it's going 45 degrees clockwise or 315 degrees counterclockwise. And since it's cosine, I'm now looking at the x value, which in this case is root 2 over 2. Sometimes you could ask the question the other way, and I could say cosine of x is equal to negative 1/2. And now my unknown is, well, let's just leave it as theta. My unknown is the angle. It's not the measurement. And if I'm doing this, I could think of, all right, where's negative 1/2 on the x-axis? That's this right here. And this one right there. So theta could equal, what are these angles? Now, let's get rid of this angle right here is 90 plus 30. So that's 120 degrees. This angle right here is 180 plus 60. So that's 240 degrees. And that's all the stuff that you have to know about with the unit circle. However, there is one other thing that is just another layer. I don't know if it's layer on top or on the bottom, but it's often layered into these problems. Is that when we go from here, we don't use degrees anymore to measure angles. We use a new thing, and the new thing is called radians. And it's just like if we measure length, we might have one measurement which uses feet and inches, and another system that uses centimeters and meters. So it's just a different way to measure a new thing. But what a radian is confusing because you grow up your whole life thinking about angles in degrees, and now math comes at you and says we're going to measure them in radians. But if you think of this circle again, still it's not that pretty, but if you think of what's the circumference going around this circle, if I were to go all the way around the circle, the circumference would equal 2 pi r, which is cool, but we actually know what the radius of this circle is, because again, it's called the unit circle for a reason. It's a circle that all of the circles can be scaled from. This one has a radius of 1. So the circumference of this unit circle is equal to 2 pi. And so because of that, we're going to call the angle that goes all the way around the circle 2 pi. So 2 pi is going to equal 360 degrees. And we can sort of think of this to help us make our next thing. So if 2 pi goes all the way around the circle, 1 pi is going to go just halfway. So 1 pi is equal to 180 degrees. And now 1 pi being 180 degrees is kind of the place that I start with. So if you list all your angles in degrees and you list them all in radians too, this is 0, 30, 45, 60, 90. And if I think of what is 0, well, 0 is going to be 0. If I think of 30, well, you can think of 30 as 30 degrees, but you could also think 30 as how many 30-degree angles could I fit in this whole half circle? And there's 6 of them, right? So we know that pi is 180 degrees, and you could fit 6 30-degree angles in 180. So I think of 30 as pi over 6. If you think of how many 45-degree angles could go in 180, you could be able to see that it takes 4 45-degree angles to make a half circle. How many 60-degree angles does it take to make a half circle? 3. How many 90-degree angles does it take to make a half circle? 2. With 120 degrees, there's no exact calculation, but you could think of what is 120? Well, it's 4 30 degrees, which is 4 pi over 6, which simplifies to 2 pi over 3. 135 degrees is 1, 2, 3, 45-degree angles. And since a 45-degree angle was pi over 4, this is going to be 3 pi over 4. 150 degrees is going to be 5 pi over 6, because that's 5 30-degree angles. 180 degrees is going to be pi. That's where we started with. And if I keep going, it's going to be 210, 225, 240, 270, 300, 315, and 330. And 210 is how many 30 degrees angles? It's 7, so this is 7 pi over 6. 225 is how many 45-degree angles? It's 5, so this is 5 pi over 4. 240 is how many 60-degree angles? It's 4 60-degree angles, so it's going to be 4 times pi over 3. 270 is how many 90-degree angles? It's 3, so it's going to be 3 times pi over 2. 300 is how many 30-degree angles? It's 10 pi over 6, but that's a fraction that we can reduce, so that becomes 5 pi over 3. 315 is 7 45-degree angles. 330 is 11 30-degree angles. And I know that's a lot. Ideally, it would have been more than one big, long lesson, but I can't think of anything else I have to say. Hope you enjoyed this.